Hello and welcome to the logic of it all. In this video, we are going to talk about the union and intersection of two sets. Let's start with the union. So we have two sets A and B, and their union is going to be this set A union B, which we represent like this, where it contains every element of A as well as every element of B. So you can think of A union B as a new set that is created by merging all the elements of A and B together into one set. Now here's an example. If A is ADE and B is C and D, then their union, A union B, union of A and B, will be everything that is in A, so A, D, and E, as well as everything that is in B, so C and D. But we have already included D, and if you remember from previous videos, repetition is not important in sets, so we don't repeat D, and that will be the union of A and B. Now, on the other hand, if you want to take the union of B with A, B union A, then we write down the elements of B first, C and D, and then we add the elements of A. So A, I'm not going to write D again because it's already included, and finally E. So this is B union A. Now, if you think about, again, the definition of equality of sets, we said that the order of the elements is not important. In other words, as you can see in this example, A union B and B union A are exactly the same sets. And if you think about this in general, this is not something specific to these two examples. For any two sets A and B, A union B is always equal to B union A, no matter what B and A are, for any two sets A and B. And this is a set identity. Another example is if you take the union of A with itself. So A, D, and E, union A, D, and E, is going to be A, D, and E, right? So, which is A itself. And again, it's not difficult to see that this is not specific to this particular A. If you take the union of a set with itself, no matter what A is, you always end up with the same set. And this is another set identity. And finally, if we take the union of B with the empty set, recall that this is the empty set. The empty set doesn't have any elements by definition, which means that it doesn't have anything to contribute to the union. And as a result, we end up with the same set B. And again, this is not specific to this particular B that we are using in this example. For any set A or B, whatever you want to call it, if you take the union of that set with the empty set, remember that this is another notation for the empty set, then you end up with the same set. So that's another set identity. So the union is commutative. A union B is the same as B union A. If we take the union of a set with itself, you end up with the same set. If you take the union of a set with the empty set, you end up with the same set. Now, this is a good time to introduce the concept of a Venn diagram, which we use in different situations when we are dealing with sets. So what we do is we usually use a rectangle to represent the universal set. You see this U here, so that's the area of this rectangle. And then for other sets, we use circles or oval shapes to represent different sets. So here we have two sets A and B. And if we want to show where A union B is, we need to shade all the area that is included in A as well as all the area that is included inside the circle representing B. So the shaded area represents A union B. So this is called the Venn diagram for the union of A and B. But there are some special cases that we can consider as well in terms of the relationship between A and B. So one of those possible scenarios is where this is again my universal set U, and this is A. And it could be that unlike what we see in this picture, A and B do not overlap, right? And in this case, if you want to shade the area representing the union, you have to shade everything that is in every area that is inside A as well as everything that is inside B. So this is A union B again, but for the case where A and B are disjoint, they don't overlap. And we can imagine another scenario as well. Again, this is my universal set, the rectangle, and it could be that A is this big set and B is a subset of A, like this. And again, in this case, if you want to shade A union B, if you want to represent the union of A and B using the Venn diagram, we need to shade everything that is inside A as well as every area that is inside B. So this will be the representation of A union B. So this is the general case. This is the case where A and B are disjoint, and this is the case where B is a subset of A. And in all three cases, the Venn diagram represents the union of A and B. All right, now let's move on to the next operation, namely intersection. So we have two sets A and B, and their intersection, A intersection B, like this, is the set that contains elements that are simultaneously in A and B. So where the two sets A and B overlap, that's going to be their intersection. So for example, if A is 12, 3, 5, 99 and B is 4, 3, 7, 12, their intersection, A intersection B, will be the set of elements that are common between A and B. And if you look, there are two of them, namely 3 and 12. Now, again, similarly, we can take the intersection of B with A, and it's going to end up with the same set. And similar to union, we can say that the intersection of two sets is commutative, which means that the intersection of A with B is always equal to the intersection of B with A. If you take the intersection of a set with itself, you end up with the same set. So no matter what A is, A intersection A is always A. And if you take the intersection of a set B with the empty set, because the empty set doesn't have any elements, it doesn't have anything in common with B. It doesn't matter what B contains, it's always going to be empty. So the intersection of any set, A, B, whatever you want to call it, with the empty set is always going to be empty. Now, in the final example here on this slide, we have two sets A and B. A contains three elements, namely D, E, and T, and B contains three elements, C, K, W, R, and Z. If you look at their intersection, they don't have any elements in common, which means that their intersection is going to be empty. And in this case, for these kind of sets where they don't have any elements in common, where their intersection is empty, we call them disjoint. We say A and B are disjoint. So this is the terminology that we are going to use. Now, Venn diagram for intersection. So again, the rectangle represents the universal set. The circle on the left is A, the circle on the right is B. Now we want to shade their intersection, and you see that that's the area that is simultaneously in the circle representing A and also in the circle representing B. Right? So the area that they overlap. Now, in the previous case, we talked about some special cases. Let's do that here as well. If this is my universal set, and this is A, and this is B, so they don't overlap, then their intersection, they don't have anything in common, so their intersection is going to be empty. We don't shade anywhere. And finally, the other case where A contains B as its subset. Now, if you think about it, we want to shade the area that is simultaneously inside the circle A as well as inside the circle B, and that will be the entirety of B, right? So this is their intersection, and yeah, so we have three cases. This is the general case. This is the case where A and B are disjoint, so their intersection is equal to the empty set. And this is the case where B is a subset of A. And in that case, as you can see from the diagram, their intersection is going to be equal to B. All right. Now, let's take a look at an example. Again, similar to the previous videos, I encourage you to do this yourself. But we have three sets, A, B, and C, and we want to look at A union B union C. Okay, so we take the union of A and B first. Let's do that up here. So the union of A and B will be everything that is in A, so C, A, T, and E. Oh, sorry, I shouldn't have closed it yet. And then we add the elements of B as well. So we add D, E is already here, and also F. So this is A union B, so that's this part. And then if we take the union of that with C, so A union B, union C, will be everything that we have so far. So C, A, T, E, D, F. And then we look at C. C has A, but we have already included A. It has E. E is already there. F is already there. So the only thing that I need to add is M. So this will be A union B union C. Now, if you do it the other way around, A union B union C, which means that first you compute B union C, and then take the union of A with that, you end up with the same set. So that's another set identity, that if you have three sets, no matter what they are, if we take the union of A and B, and then take the union of that with C, that's always going to be equal to taking the union of B and C, and then taking the union of A with that. Okay, so that's another set identity. Another example, A intersection C union B. Now, for people who are doing this for the first time, I always encourage them to do this step by step. So first we do the intersection. So let's see, what is the intersection of A and C? The intersection of A and C, what do A and C have in common? They have A in common and also E in common. Now that we have A intersection C, we can take the union of that with B. So we write A and E, which we already have, and then we look at B to see if it has any new elements to be added. It has D, we add that, E is already here, and also F. So A, E, D, F is A intersection B union C.